Good morning, meteorology class. Um, I am going to be going over your flip grids and submitting feedback on your diagrams today. I know a lot of people had some difficulty from the ones that I have seen. I just want to let you know I'm going to keep on rolling with it. We'll see how things go. If you can do some modifications, that's probably the way that I'm going to go. In the meantime, I want to continue with something that I think is a lot more digestible. The original plan was for us to work on a lot of those diagrams in class. So um, it's challenging to learn how to do those diagrams without kind of hands-on feedback. The chapter that we're moving on to now is air pressure and winds. That is an area that we can, kind of go back to the textbook, work on some reading, and I'm going to post something similar to these notes. Um, this is to kind of just supplement what you're going to already, do in the reading. The better kind of visualization you can get along with this, I think it makes learning it a lot easier. All right, so we're talking about pressure, but we're kind of already familiar with that. But what happens with pressure and winds? Why do we get changes in pressure? What happens when our pressure is changing? And so, one of the things that we have to keep in mind is that our temperatures are varying, right? Our lapse rate, in general, there's lots of variations in temperature all over the planet. At the same time, the atmosphere is a fluid, just like an ocean or a pool. You can get surges and higher areas than others, and it's going to, move around over time. So before we look into comparisons, let's just remember how we think about pressure. Now, when we just were talking about surface pressure, we're talking about, well, the pressure that you experience here at the surface is the result of all the air that is above you. That's why as you move up in the atmosphere, the pressure decreases because the pressure is really only due to what's above. So the tops of these buildings here are experiencing less pressure than the bottoms. The atmosphere is not very dense, so we don't end up having noticeable amounts of pressure change. But if you've ever driven in the mountains, you may have realized that, you feel that pressure in your ears. Well, that's because you're moving up and down, and the atmospheric pressure that you're experiencing is changing. So now we gotta kind of incorporate what we already know about temperature with what we think about of pressure. Um, we know that warm air is less dense, cold air is more dense. And so we can think of some cities that are separated by some horizontal distance. So, they're next to each other, but they're not necessarily completely in the same environment. Now, if they have the same temperature and pressure to start with, then we wouldn't expect any kind of flow of air because there's no difference in pressure, right? The difference in pressure is what's going to generate be a driving force of creating our winds. Now, if we think about what's happening if, say, one of these cities starts, heating up, all right. Now, basically, or the other one gets colder. What we need to keep in mind is we're talking about the same amount of air. What's different is the density and the height of that column of air. So if you're looking at City 1 now has a shorter air column. All right, so we could imagine that this is just a representation of the atmosphere, all the way from the bottom to the top. So, if you went and counted all of these, little representative air molecules, they'd be the same. The difference here is that they are closer. On the other hand, the warmer city, right, they've expanded, the air has expanded, and so these air molecules, the same number, are higher now. And even though the pressure you'd experience at the bottom is the same, because if I look at the bottom here in situation A of both cities, the bottom here in situation B of both cities, I have the same amount of air above me, so the surface pressure is going to be the same. But the difference happens when we start looking at what happens when we move up, right? As I move up in the colder city, I see that the pressure is going to change more rapidly, because now that I have a shorter air column, you could almost say I pass more air on my way up than I do in the warm city. So at the base, I might have the same pressure, but if I look up here, right, at altitude, well, now I've got a lower pressure at the top of my cold column than I do of my warm column, because my warm column, I still have a good amount of air above me. And so you could almost say that the atmosphere is thicker above City 2, in terms of like the distance from the bottom to the top, even though the density is less. I know there's a lot to digest there. The point is, as you move up, the pressure decreases more rapidly in the cold column. That means that when I go up to altitude and I compare the same height, well, now at altitude, the warm column is going to have a higher pressure than the cold column, and so you're going to get upper air movement from high to low. Now, once these molecules start moving, you're changing the amount of air that is in the column. And so if I took, some of these little molecules, and I can't move them around, but if I took these molecules and started moving them over here, well, now we'd have to think about what happens at the surface. As I'm adding air at this altitude, that means the pressure in City 1 is actually going to be increasing at the surface. The pressure in City 2 is going to be decreasing as air moves. All right, so this is where we start to get this cyclical motion, because if I have air leaving, going from City 2 to City 1 at altitude, well, City 1 at the bottom is going to have a higher pressure. City 2 at the bottom is going to have a lower pressure, and so then I can get different motion, right? Motion, kind of pushing things back on the other side. That's another reason why we can kind of see that, another driving force of, say, convection, having rising air and sinking air. So as you're, going through the reading, I really suggest you kind of come back and look at this and try and piece together what it's trying to tell us to do, right? So, again, once we actually move air from column 2 to column 1, the pressure is going to be higher at the surface. Well, pressure, winds flow from high to low pressure. So now I'm going to go from high to low down at the surface. So again, you can kind of remember relative, at the same height, this would be considered a high pressure and this would be considered a low pressure. But that's only comparing at the same height. No matter what the temperature of your atmosphere is, you're always decreasing in pressure as you go higher. All right, so even though I might put a H up here for high, that's only mean in reference to, at this altitude, it's higher in City 1 than it is, or sorry, it's higher in City 2 than it is in City 1. But obviously, the pressure at altitude is always lower than the pressure at the surface. Because even though and then the question is, well, if it's always lower, why isn't just all of our air going up? Well, it's because of gravity, because gravity works against that. So when we talk about the pressure, well, the two things that are really affecting the pressure are the temperature of the air and the density of that air. So that's not something I want you to focus on right now. Now, just over time, right, we do observe different temperature and pressure swings. We can kind of see that over time, right, starting in the morning, our pressure, our surface pressure typically increases over the course of the day as the temperature rises. And then, as the pressure over the evening time, the pressure is going to decrease, and that's like what we experience, what mid-latitude areas experience. On the other hand, in the tropics, they're much more affected by things like the tides, and so as the tides go sloshing around, it moves the air, and so we get a different kind of overtime temperature pressure profile. The pressure kind of rises and sinks throughout the day. Now, maybe you remember back to chemistry and you measured, or one of our units of pressure was millimeters of mercury. And millimeters of mercury, we typically think about it as our usual unit is millibars. You can kind of see these are just some examples of different types of pressures that are observed. You see a deep low pressure system is only at about 980 millibars. All of these other values are super low, but those are what we observe in the center of hurricanes and tornadoes and things. And then, the very upper limit of our pressure is 1090, and so that's kind of why we're able to use that rule of if it's closer to 1,000 on our surface weather symbols. However, you can put a 10 in front of it. If it's a 90 or an 80, you're going to put a 9 in front of it. We will not be observing this kind of pressure 1090 ever. And so again, let's just think about what's going on in terms of pressure in these different devices that are designed to use it. So a barometer is something that measures the atmospheric pressure. So what happens in a mercury barometer, right, and there's no air up in the top of this tube to push it down, the air actually, like as the air pressure increases, pressure is force over area, so it's going to exert a stronger force, and it's going to push this mercury up until the force of gravity stops it. The force of gravity of all the mercury that's above. That's kind of like our atmosphere, right? We might have more pressure at the bottom, and it might be trying to push up, but there is a force of gravity pulling this back down. These devices are very, very sensitive because not only can pressure change how much mercury is in this barometer, but so will temperature. So if you're going to use this, you have to use this in a constant temperature environment. This is another example of a barometer. It's an aneroid barometer. And in this little, this is not metal, this is like a little pouch that actually just has a fluid with a little bit of air in there. And as the air expands and contracts due to changes in the atmospheric pressure, it's going to move this a little bit, a very small amount. But due to these levers, a small change in this pressure and the size of this pouch here, the cell here, is going to move the needle, exaggerate that motion so that we can easily see the difference between our different pressure levels. If this was a direct relationship, all of our numbers would be crammed into like a half of an inch there. And then, this is another aneroid barometer that just records it over time. So I think that is enough for you to digest today. I don't want to, give you too much. I'm going to try and post some office hours. I hope that this was informative. Make sure that you're doing the reading assignment, and I'm going to have you answering questions out of the textbook. If you do not have your textbook, email me and I'll start scanning